Welcome to a tutorial on circuit theory, and today we're going to discuss about the first order RC filters. Okay, so here the filters that we're going to show, okay, are basically based on simple resistor and capacitor designs. Okay, so we'll start over here with the low pass RC filter. Okay, so let me just write it down over here, low pass filter. Okay. So I'll just show you the picture before we go deeper into this topic over here. Okay, there you go. Here's the picture of the low pass RC filter. Okay, so you can see here, on the left of this figure over here, okay, these are the input terminals. So let me just name them over here. Let me just name them 1 and 2. So over here, the terminals 1 and 2 are the input terminals. So if we just go forward and apply an input signal right over here, let's just call it Vi, okay, then we're supposed to obtain the output signal across that of the capacitor right from this place. So let me just call this as terminals 3 and 4 respectively. Okay, so here we're going to get the output voltage, that's VO. Okay, so the basic question is that how this circuit works. Okay, fine, I can understand that, but let me just tell you before that, this input signal which we are applying over here, this is obviously not a DC signal. Okay, it is of course an AC signal, so it can have some sort of frequency. And let me just tell you that in case of filters, the frequency always matters, because here we're just calling this filter a low pass filter because this sort of filter can only let pass a certain range of frequencies, okay, which is obviously lower than its cutoff frequency, which is of course given by we just denote it with the symbol FC, and that is always equal to 1 by 2 pi RC. Okay, so this is of course the cutoff frequency of all sorts of RC filters. Okay, so be it a low pass filter or a high pass filter, it doesn't matter. This FC always represents the cutoff frequency of a first order RC filter. Okay, so now, as I said, in case of that of a low pass filter, okay, this cutoff frequency obviously determines a sort of boundary where the frequency ranges, or rather all the various types of frequencies that come below the value of this cutoff frequency over here, will be allowed to go out as an output signal across the terminals 3 and 4. But with those that are above the cutoff frequency level, okay, those signals won't be allowed to be output across the capacitor. So that's quite interesting. So this circuit over here only lets output that part of the signal, okay, or rather those signals with frequencies below that of the cutoff frequency. Okay, so let's just study this in a little detail. Okay, so now since we have let's pull the page down a bit first. Okay, so now since we have assumed here that the input signal is of course given by the term Vi, okay, so let's just, obviously it's quite natural that a current over here would be generated due to the application of this input signal Vi over here. So let's just call this current as small I. So in that way, if we just try and find out the impedance of this circuit over here, so the impedance would be given by Z as equals to this will be given as XR plus XC. Okay, and if we just since the capacitor over here is of course a complex, has a complex reactance, so we can just basically term it somewhat like this. Okay, so, or rather, if it would be better if we could just simplify this whole thing and represent it simply as R plus JXC. Okay, so here that's the impedance of this particular circuit, and if we just take the modulus of this impedance over here, we're going to get root over of R squared plus XC squared, which would be equal to R squared plus that of 1 by omega square c square. So there you go. So now, as you can see over here in this particular circuit, of course, okay, in this particular circuit over here, we're supposed to find the output across that of the capacitor. Okay, so in order to do that, it's quite necessary to to find the output voltage drop across occurring across the capacitor. So in order to do that, we'll just basically find out the voltage drop across the capacitor, so which it would obviously be given by I multiplied, that's the current in the circuit over here, I multiplied by the capacitive reactance, which is, of course, well, let's just take its mod value. If we just take the mod value of the capacitive reactance over here, we're supposed to get 1 by omega c, since xc is just given by, well, 1 by j omega c. Okay, so here we're getting it as, well, I multiplied by 1 by omega c. Or rather, we can just basically write it as multiplied by modulus of the capacitive reactance, and we get I multiplied with 1 by omega c. Okay, so, and what about the value of I over here? Well, I over here could be obtained as something like this. The current in this circuit would be given by the input voltage, well, divided by the modulus of the impedance which we obtained. So it'll be equal to VI divided by root over of R square plus 1 by omega square C square. So that's exactly what we had found over there for this impedance, as you can see. Okay, so now we just go back to this particular equation over here again in terms of VO. So if we just put this value over there, we're gonna get it as equals to, well, VI multiplied, VI divided by omega C, the whole thing divided by, well, root over of R square plus 1 divided by omega square C square. So that is exactly what we are going to get over here. Now if we just go forward and try and modify this equation, okay, let's just call this one as equation 1, and if we just go forward and try and modify this thing, then we're going to get the V output as equals to, well, VI divided by root over, there you go, omega square R square C square plus 1. This is exactly what we are going to get. Okay, so now let's just keep this equation in mind. So this is exactly the equation which we were searching for all this while. So let's just make it equation number A. Okay. Well, so if we just try and decipher the physical significance of this circuit based on the equation A, then we can well understand that in this particular circuit, well, as we go on increasing the frequency, since we know that, well, omega is given by 2 pi f, so if we go on increasing the frequency over here, if f tends to infinity, well, in that case the whole term at the denominator of this particular fraction over here would become infinite as well. So anything by infinity is obviously 0. So as f would increase, well, the output voltage would begin to decrease. But on the other hand, if f tends to 0, okay, if f tends to 0, so if f goes on to decrease, then we'd have this, the value of this fraction would be obtained as equals to Vi. So we'll basically have under this situation, well, under this particular situation, we're basically going to have, well, V out, over here, the V out equals to that of V in. And in the previous case, it would be V out equals to 0. Or rather, this will basically tend to 0. Okay, so these are the various sorts of ways in which you can basically find what the circuit response would be, or rather understand it that way. So probably is the easiest one. So over here, this expression which we had obtained as equation A, well, it could be modified also in terms of the frequency given by f. Okay, so if y'all go back to the previous part again, and well, if y'all would just take into account that the cutoff frequency is given by fc over here, then in that case, well, we can just basically modify this equation in order to obtain something like this, as well, VO equals to VI divided by root over of, well, 1 plus f by f0 squared. Okay, so there you go. So in this particular expression, we can just basically well, modify it as this particular expression, as you can see, and we'll just call it, well, equation B over here. So that's in terms of frequency. And if we go on and further modify this whole thing somewhat like this way, well, V out by V in as equals to 1 by root over of that of 1 plus f by f0 squared. Okay, and well, we can basically well, term it as the gain of the circuit, which is of course a ratio between the input and the between the output to that of the input applied to the circuit. So in this way we can just basically obtain the relationship for gain, and let's just call this one as equation C over here. There you go, that's the equation C. And well, in that case, if we just go forward and put, well, F equals to FC. Okay, let's go back over there. Okay, so here you go, that's FC down below. So if we go forward and put F equals to FC, so let's see at F, okay, at F equals FC, what should be the response? Well, at F equals FC, well, the gain over here would be equals to 1 divided by root over of 1 plus, well, FC divided by FC. So if we just go forward and well, calculate this, we're going to get something equals to 1 by root over 2. So which means the gain would fall down to its 1 by root over 2 at level, or rather we can also express it in decimal as 0.707. Okay, so the gain would basically, gain of the circuit would basically, fall back to its 0.707th part of its maximum value if F is equals to FC. So at the cutoff frequency, basically the gain of the circuit falls to about 0.707 part of its value. So we could basically represent this with a graph. Okay, we have the graph right over here. Well, as you can see, this graph actually represents the ideal, or rather the theoretical response. That means a response which the low pass filter is, well, theorized to have. Okay, so this might not be the actual story, okay, whenever you're going to practically implement this circuit. So you can see over here that, okay, fine, I'll just choose a different color. Okay, so you can see over here we have a well, gain versus frequency graph. So this obviously is a gain, okay, versus the frequency graph right over here. And of course we have, well, various bands of frequency ranging from 0 at the origin to, well, it continues throughout. So you can see here at the particular frequency level that is represented by the cutoff frequency that's denoted with the symbol FC, okay, the signal, or rather the gain of the low pass filter just suddenly falls to 0. Whereas at frequencies well, lower than that of the cutoff frequency, the gain was, well, it was okay, it was at 1. So which means that the input signal was equal, the output signal was almost equal to the input signal at, well, these frequencies which were basically lower than that of the cutoff frequency. So we'd basically call the ones, the frequency bands which are actually being, well, output, okay, at which the gain is of course at the level 1, okay, we'll just call that band of frequencies as the pass band. Okay, so here we have the pass band, which is of course the lower frequencies than the cutoff frequency. And on the other hand, we have the other frequencies that are, well, higher than that of the cutoff frequency, and they're obviously not allowed to be output. Okay, so we just call this part of the frequency range, okay, we'll just call this part of the frequency range as the, well, the stop band. Okay, there you go. Of course, so this part of the frequency band lower than the cutoff frequency is the pass band, and on the other hand, the one above the cutoff frequency is of course the stop band for a low pass filter. Okay, so as I said, this was the theoretical response. So let's take a look at the practical response. Okay, there you go. So here we have the practical response. Now we are dealing with a first order low pass filter only. Okay, so you can see over here that, well, this is of course a gain versus frequency curve again. Okay. Well, in this graph, if you would obviously observe closely, we have the gain plotted in terms of decibels. So I'll just write it over here. So this is of course the gain in decibels. Okay, so decibels. There you go. So we can obviously see over here that, well, at gain equals to 1, well, that's represented as the 0 decibel level, and over here we have the cutoff frequency where the gain falls down to about 1 by root 2 times of its value, or rather about, well, 0.707 part of its maximum value. Okay, so you all can see over here that this point over here is represented as well as the -3 decibel level. So it's also known as the 3 decibel level. Okay, so just write it down over here. So this is known as the 3, or rather this gain over here is known as the 3 decibel gain for the very same reason. Okay, so apart from that, we can see here that there are 3 curves. Okay, so the slantest curve, the one with the gentlest slope, okay, is of course the one with the order 1. So since we're dealing with the first order RC filters, RC low pass filter over here, so probably we're gonna get this particular curve. Okay, so if we just go on increasing the order of the filter, then of course you can see, well, the slope becomes steeper. Okay, the curve's slope gradually becomes steeper. It's a little steeper in case of the order equals to 2, and then even steeper in case of order 3. Okay, so, well, that said, let's just, we just come to the end of our tutorial on the response, or rather the response of the low pass first order RC filter. So hope you've enjoyed our tutorial, and see you in the next time. Until then, it's just a very short goodbye for now, and thanks for watching.